Alright, so we will switch gears today and we will move into the next chapter. This is internal flows. So it is really like we will predominantly look at pipe flow, look at heat transport, mass transport during pipe flow. So suppose let us consider a tube, okay, and we have a fluid which is flowing through this tube. Let us say that u naught is the velocity with which the fluid is entering the tube, okay. So let us assume that it is a flat velocity profile. Before it enters the tube, and if I put coordinates, if I call this as x direction, so this is x less than 0, so it is a flat velocity profile, and if I mark the midpoint, so the radius of the tube is r naught and the diameter of the tube is d. Okay. So now suppose if we, let us say the fluid flows into the tube, okay. So similar to flat plate, the fluid is, note that it is a circular tube, so it is a circular cross section, it's a circular cross section. So as soon as the fluid enters the tube, it experiences a wall which is present at location r naught, right. So similar to the flat plate, the velocity of the fluid will come to 0 at the wall, right. So u at r naught, that is equal to 0. Okay. Now suppose if I say v is the radial component velocity, so u is the x component velocity and v is the radial component, radial velocity component. So of course v at r naught is also 0. Okay. So note that it is a flat velocity profile, which means when before it enters the tube, the fluid is primarily moving only in one direction. But as soon as it touches the wall, as soon as it experiences the wall, suddenly the fluid comes to rest, and so the viscous effects will start playing a role, and therefore the fluid will start moving in both directions, both radial and the axial direction, okay. And therefore it results in a formation of boundary layer. So that is the boundary layer. So what you see here, the location in between, so note that it is a circular tube, so the boundary layer will be present in every location in the rim of the tube, okay. So and they will slowly merge and converge together at a certain location. Now in this region here, the fluid will continue to be flowing as an inviscid fluid, because the viscous effects due to the presence of the wall will be experienced slowly and gradually as the fluid goes inside the tube. Okay. So at some location where these boundary layers merge, and after a certain point you get what is called the fully developed regime. So fully developed regime is a location where every location in the fluid, every location inside the tube, the fluid experiences the presence of the wall. So the viscous effects will start playing a role at every fluid particle in any cross section after the fully developed regime. Okay. So there is no inviscid flow regime after the fully developed location all the way to the end of the tube. Now suppose if I draw the velocity profile, okay, let us say at position x1, if I draw the velocity profile, okay, so this is the location of the boundary layer. Okay. So if I draw the velocity profile, it will be maximum, the maximum will be somewhere at the center. So you will have a profile which looks like this. It has to be symmetric. So it's a symmetric velocity profile. So it should be flat velocity So between the boundary layers, it will still have same velocity profile as the fluid, as that of the fluid which is entering the circular tube. So it will have a flat velocity profile between the boundary layers, and then the fluid will be retarded in the boundary layer. And so you will have a velocity profile which looks like this in the x direction. So this is the x component velocity profile at x1 location. Okay. So now if I look at the profile, so this is the profile at x1 location. Now if I look at the velocity profile after or at the fully developed regime, what I will have is a parabolic velocity profile. So this is x fully developed regime. So anywhere after the fully developed regime, the velocity profile will continue to remain the same as long as you go inside and as long as the regime changes. So you could always go from laminar, if it is laminar regime or a turbulent regime, the profiles are different. So let us assume that we are looking at laminar profiles. We have laminar regime, then you will see that as soon as you cross the fully developed regime, the velocity profile does not change anymore. Okay. So now, simply based on this intuition, we can actually detect a lot of interesting properties. Okay. So the first thing is that, so between x 0 and x fully developed regime, okay, so the velocity in the radial direction is not 0, and not just that, du by dx is also not 0 in all locations. Remember that before it enters, du by dx is 0 because there is no change in the velocity and it flows at a flat velocity profile. But then if x is greater than fd, that is if you reach the fully developed regime, so suddenly you will see that the y component velocity goes to 0, okay, and then you will have du by dx also will be 0. Okay. The velocity profile does not change, the fluid will continue to move in that direction, but it will have a definite parabolic profile. So here if you see before the fluid enters in this region, you will see that du by dr is also equal to 0 because you start with a flat velocity profile. But what has been introduced because of the presence of the wall and because of the retardation of the fluid, because of the viscous effects, so du by dr is not equal to 0. Okay. So this immediately means, so this immediately implies that the velocity, x component velocity, is now a function of both x and r. So that's an immediate implication. Okay. It's now going to be a function of both x and r. So with this, let's see what to do. So in the flat plate case, we always had a reference velocity. Okay. So in a flat plate case, there existed always a reference velocity, which is basically the free stream velocity. But in a pipe flow, there is nothing called a free stream velocity, right? So in a flat plate, you had whatever fluid flowing well past the boundary layer, you say that's a free stream velocity, and we use that for all scaling purposes. But in an internal flow, when fluid is flowing through a pipe, there is no reference velocity. So we have to start from defining the reference velocity. So what's the most appropriate reference velocity? Yeah? Yes, any suggestions? U naught? No, but that's before the pipe, right? So what's the best reference velocity inside the tube? Maximum at the center, okay, that's one possibility. Okay, what else? Average. Why average? Because at every cross section. So we can define an average flow rate. So there are two reasons why it is a good measure. Okay, one is volumetric flow rate is constant if it is a steady flow, right? So again, if it's a steady flow. The steady flow is constant at every cross section. That's very important. But more important than that, much more important is that if I say I put a measuring device, a flow measuring device, okay, at the end of the pipe. Okay, let's say I know how I put a rotameter at the end of the pipe, or I put some other meter at the end of the pipe, okay, or a venturi meter, for example. Okay, so now what I can measure, or what I would measure, is actually the average flow rate. So when I put a flow meter at the end of the pipe, so note that the profile doesn't change after the fully developed regime. So I can measure, that's a very important point, you can measure the average flow rate. So remember that the whole course so far, we always said that anything you use as a reference has to be something that should be a measurable quantity. Otherwise, it doesn't make much sense to use it as a reference. So average flow rate is actually one of the good measurable quantities. In fact, we will see in heat transport case that the average temperature is also a very good measurable quantity. Okay. Alright, so we can now, so we have to define this quantity because we do not know what it is from a theoretical point. Yes. Du by dx is 0, yeah. U is, well, actually after this location, you're correct in observing that U is not x dependent, and we are going to show that rigorously that it's not. Okay. So right now we don't know anything about where this x fd is there. Before this point, you are correct in observing that before this point U is a function of both x and r, and after this point it's only a function of the radial position. You will see that in a short while. Any other questions? Okay. So now we need to define what is this average velocity, and we have to use that as a scaling parameter for all the modeling equations that we are going to write. Okay. In order to define the average flow rate, we are going to use the first observation that the volumetric flow rate is a conserved property. Okay. So now we can define m dot, okay, which is the volumetric flow rate at any cross section, is basically averaged over the whole area, density into the local velocity, okay, local velocity into DAS, right. So that's the differential cross sectional area. So that's the density of the fluid, that's the local velocity multiplied by DAS integrated over the whole cross section will tell you what is the mass flow rate at any location in X. Okay. So now we can define this, okay, as rho into, so that's a definition. So um is the average velocity, and in fact I put m here because in classical literature it's also called as mixing cup velocity, called cup mixing or mixing cup, either way it's used. Mixing cup is basically area average or cross sectional average quantity is called mixing cup quantity, that multiplied by the cross sectional area AC. Okay, so that's a definition. So from here we should be able to find out what is UM. So UM is 1 by rho AC integral over the cross section rho U into dAC. What is dAC? What's the differential area in a cross section? Come on, 2 pi r dr. That's not hard. So if I draw a cross section, okay, and if I take a small annular element inside, and if this is at location r, and this thickness is dr, so the area of this shell is 2 pi r dr. Okay, so I can plug that in here. UM will be 1 by rho. Area of cross sectional area is pi r naught square, because r naught is the radius of the tube, integral 0 to r rho u 2 pi r dr. Okay, so that will be 2 pi by rho pi r naught square integral r naught r dr. So now if I assume that it's an incompressible fluid, so suppose if I assume that it's an incompressible fluid, then the density doesn't change, and so I can pull the density out of the integral. So UM, which is the cup mixing velocity, that will be 2 by r naught square integral 0 to r naught u r dr. So that's the definition of the mixing cup or the cross sectional average velocity. Now this is valid at every location. If it is in a fully developed regime, then u is not a function of x position after the fully developed regime, but before the fully developed regime, u is a function of both x and r, and therefore you have to consider the whole dependence of radius at all locations starting from 0 to if L is the length of the tube. So UM is a quantity which actually does not change with position after in the fully developed regime. Okay. So the average does not change with x position, and so it's a good reference velocity. But if you need to find UM, you need to know what u is, right? So if I don't know what the local velocity is, at least in a fully developed regime, then I will not be able to find out what is the average velocity. So the next exercise is to find out what is the velocity profile at least in a fully developed regime. Okay. What is the velocity profile in a fully developed regime, at least in a fully developed regime? Okay. Okay. How do we find this? Yeah, Navier-Stokes equation. Well, that's too complex. That's true, Navier-Stokes equation is valid everywhere in the tube. If you solve them, you should be able to get it. There are some simpler ways to do that. What are the forces that are acting in a fully developed regime? Let's draw a pipe. So suppose this is my fully developed regime. What are the forces that are acting on the fluid particles in the fully developed regime? Pressure and viscous forces, right? So if I can make a balance between the two, I'm done. So what we are going to do is we are going to make a balance between the shear and pressure force. So if I can make a balance, I am done, right. So now if I take a shell, annular, so I will draw the cross section. Okay, so if I have an annular cross section, okay, and let us say that so this is dx and this is dr, equivalently here this is dx, okay, and this is dr, okay, and this is located at some r position, okay. So if the small shell is located at some r location, and I can make a force balance. So supposing so if I take this box here, so if supposing Px is the pressure that is acting on that element in that location, and if the pressure that is acting here is P of x plus dx, okay. So this I can write as Px plus dP by dx into dx using Taylor series expansion, and if the shear force acting is tau rx, and this will be tau r plus dr x, okay. So I can make a force balance now. So what will be the balance? Be tau r is acting on what area? What's the area? 2, yeah, be careful, it's an annulus. So it's a circular annulus, right. So the inside area is 2 pi r into dx, right. So the area in which tau r is acting is 2 pi r into dx, okay, minus tau r plus dr, I can write it as tau r, so that will be 2 pi r plus dr, sorry, 2 pi r dr into dx, okay. So that's the shear at the outer end of the shell, okay, plus I can write the pressure forces. What's the area at which it is acting? 2 pi r dr. So note that it's a annulus, right. So 2 pi r dr is the area of this annulus shell, okay. So that will be 2 pi r dr minus P x into 2 pi r dr plus dP by dx into 2 pi r dr into dx. So that's the, and that should be equal to 0 under steady state.